So in the last class we started to talk about the logistic regression. The logistic regression is the key idea behind logistic regression is the log likelihood function. Okay, so the we need to think about it. We have so again we have theta x1 up to xp, and you have a y. Okay, and then you have the subject 1 to up to like n. Your X matrix, okay, your X matrix design matrix is just like the normal, the same as your linear regression. It's n by p design matrix. The only thing now is your response variable y. Okay, y is no longer continuous, rather. Sure. On the right. Okay. So the thing is the y now is binary. Okay, it's no longer the continuous. So the model that we have in the density function for the y for the yi for each of the subject I density function. So we assume yi is follow a binomial 1 pi r. This is the binomial model, right? As assume each subject has just its own the category. So this is this is also the Bernoulli distribution. So the density function for the yi is going to be yi to the power equal to the pi I to the power of yi times 1 minus pi I to the power of 1 minus yi, right? So this is a binomial. So in that case, basically saying the probability yi equal to 1 is pi I, y equal to 0 is 1 minus pi. So that's exactly the same. So therefore, the density, the log likelihood function basically is a product of everything from all the subject, and then each subject is taking its a density function. So in this case, it's just equal to the pi I, the product. Okay, this is the product pi I to the power of yi, 1 minus pi I to the power of 1 minus y. Okay, so this is our likelihood function. Then the modeling part, so-called logistic regression, the modeling part is coming to, we're going to model the pi I, right? So we want to model the pi I. So we say the logit of pi I is equal to x beta. Okay, now I'm just writing in the matrix form. So xi transpose, or like this way. So in these cases, we kind of model the success probability for each subject I, which is pi I, this is related to your features, right? Your features. So this is a prediction part. So given that, then we can say the pi I going to equal to e to the power of xi. Depending on I, you view it as a column vector or the row vector, you can have the transpose or not transpose, but it's so that's sometimes it's context dependent, right? So you know this is the xi beta, it just become a scalar. It's a linear combination of these features. So once you have this model for the pi I, then essentially what you do is you just plug in this pi I into the likelihood function, okay, and then maximize it, maximize log likelihood. Maximize likelihood function, then you're going to solve for the beta. Okay, so this is how the logistic regression is about. So then once you plug in, then your likelihood function then essentially is a function beta. Now to the thing is when we try to maximize the likelihood function, usually is difficult because the likelihood function involving a product. And then this is everything is linear or is nonlinear. Then if you try to using the gradient method to solve for the maximization, you have to take the derivative of the likelihood with respect to each beta. Then it's going to be very difficult to evaluate the gradient. So therefore, what we do is in practice we're taking the log of likelihood. Okay, this is using small l. This is below the log likelihood. So maximizing, okay, so therefore, but then the thing is maximize the log likelihood essentially is equivalent to maximize beta respect to the likelihood function. Okay, they're the same because log function is a monotone increasing function, right? So therefore it doesn't change the maximum point. So therefore the problem now is now the problem now is changing to we want to maximize the log likelihood function with respect to beta. So log likelihood function is if you just simply to plug it in here, then there you can see we just change the product to the summation. You have in the yi times the log of pi I plus 1 minus yi times log of 1 minus pi I. Right? So then again you can also plug in this is pi I into this is a log-like function, which is to become a function beta, right? So then you can work on that. So this is kind of this is where we kind of left from the last class. So this is a big picture, right? This is a big picture for log likelihood. For the all the rest are just technical details. Okay, you just figure out how to maximize it. Then we kind of like went through this log likelihood when you're taking the summation, right? You're taking the log on the likelihood function become log likelihood until then this is a product becomes summation and the merge terms and put them together. This is plugging in the pi I with this form into the log-like function. This is what we have. Then we can if you're taking the first derivative of the log likelihood with respect to each beta, right? To each beta a, this is a from like say 1 to p. Then this is the form we have. And then the second order derivative of the log likelihood with respect to beta a and beta b. Then you go through it. This is what we have, right? So this is what we left. To maximize the log likelihood, okay, to maximize log likelihood, or we want to employ a method called Newton-Raphson, okay? So Newton-Raphson is basically a numerical method, okay? I hope you guys at least have heard of this Newton-Raphson before. It's a pretty common numerical method for the optimization problem, okay? If you but if you haven't heard it before, this is sort of like one slide introduction to the Newton-Raphson. Okay, hopefully this is you can get in this is get an idea for Newton-Raphson. We will also spend a little bit time talk about like the basic stuff of optimization probably in the next week as well. Because I do realize this is a class that we have a very diverse background. Some students have pretty strong mathematics background, so this is kind of like a Newton-Raphson, this is a gradient, those ideas are easy to them, but there are also a large group of students who does not have enough background to understand algorithm. So I will have some sort of like introduction to optimization next week. Okay, so if you are not that clear about the details here, you probably can wait a little bit. I think this slide itself, okay, is clear enough. But if you, in case you have some like details, okay, then you can wait for the next week for some clarification. So the goal, okay. So now the goal is just like say in general. Okay, in general, this is a Newton-Raphson is not a method for solving to maximize the log likelihood, but in the Newton-Raphson is the general method. Okay, it's a general method. Say in this case, so the goal is we want to maximize, okay, L beta with respect to beta. Okay, regardless of the form of this L beta, but you need to have some reasonable assumption, right? Like continuity, right? So you have the first order derivative, second order derivative. So you still have some the regularity conditions But those conditions are typically well satisfied for the modeling problem, okay? Because when we do this, is like our likelihood function is continuous, right? So it's well behaved. So in this case, is like usually for the problem you see in this class, the assumptions are typically met. Okay, let's just say assume everything is all the conditions met. Okay, but we just focus on the big idea. So the way to maximize it, okay, the way to maximize is to using a Newton option is you assume you're starting from some point, okay? You assume you're starting from one point. And then what you want to do is you want to say you're starting from some estimation beta t, okay? Now, if you can somehow guarantee, okay, you can update this beta t to beta t plus 1. Right? So if you can update the beta t to beta t plus 1, you see you're starting with some like a step t, you have some like estimate gas for the beta, right? Which can maximize the likelihood function. Now, if you can find a mechanism which is you're gonna improve this beta to beta t such that, okay, this is st such that L beta t plus 1 is bigger than L beta or bigger or equal to beta t. Okay. If you can find a mechanism such that whenever you have in the beta t, then you can update the beta t to beta t plus 1, such that L the L function, which is the target function, right? The function evaluating the beta t plus 1 is always bigger than or equal to the L function evaluating beta t. If you can guarantee that for every single step, okay, then what you can say is your L is always gonna be monotonically long, at least a long decreasing, right? It's a long decreasing sequence, okay. So eventually, it will reach to some point, which is no longer, you cannot improve anymore, okay. And that point is gonna be your maximum point, because this is basically saying your function is like this. Then you're starting like a random guess. You're starting a point like this. The beta t, you can update it somehow with some algorithm. You can update beta t plus 1. So beta t plus will always like increasing. Then you can do this again and again until it reaches to the maximum. Then you cannot increase anymore. Then that's your maximum point, right? So this is sort of like the idea behind the option. The goal is, how can we find such beta t plus 1? How can we update this beta at each step such that this condition is satisfied? Okay. But before we go in that, there's a caveat. Okay, there's a caveat about this Newton option. Just based on the procedure I described, can anybody like identify a caveat or like a drawback for this Newton option? You see there's potentially there's an issue. Anybody see any issue in this algorithm? Okay, so it all looks good, right? Because then if you can find an algorithm can go up to the top, and at each step your target function is going to increase in by value, and eventually going to get into the maximum, right? Now there's one thing, right? There's one thing, because this is I want you guys to keep that in mind at the very beginning. If this is the first time you see this method, this kind of method is called greedy method. Okay, it's called greedy method. Why is it greedy? The greedy method basically means at each step you want to improve your function. Okay, that's the greedy part. Now, what's wrong with that? Well, there's nothing wrong with it, but there are potentially there's a drawback is your maximum, depending on your target function. So your maximum could just be local maximum. Okay, say for example, your function is somehow looking like this. Okay, then if your first point, if you're starting somewhere in the if you're starting somewhere in this in the neighborhood is further away from between your starting point and your global maximum. In the between, if there's a local maximum. So guess what the algorithm is going to do? The algorithm is going to climb. Okay, it's going to climb each time, climb up to this top. Okay, then up to this top, it will not move anymore because the algorithm thinks I already find a maximum, right? Because if like in this small neighborhood, I move this way or move this way, my value is decreasing, so I find a maximum. So therefore, it will not going to find this. This is a global. This is a global. This is a local, right? This is a So the Newton-Raphson method. I want you guys to remember this is at the very beginning. This is a method is a greedy method, and the maximum is going to is a local maximum. Okay, it's a local maximum. Now, if your target function is unimode, okay, is unimode, then this environment is perfect because then what you're going to see is your unimode basically means you only have one maximum point. So in essence, the local maximum will be the global maximum. Okay, so that's the fortunately in statistics, a lot of modern problem is this is if you have this is called the concave function, right? A lot of this is indeed the function is concave. Okay, if it's concave, then your Newton-Raphson is going to give you the local maximum is a global maximum. So that's just one thing I want to mention. Now, so the goal is okay, so now I hope you guys get an idea. Okay, this is sort of like the core idea behind Newton-Raphson is we want to find a sequence such that we want to update this beta in such a way then the function value is increasing. Okay, now how do we do that? Let's say you have L beta, right? Then this L beta, if we can, if we evaluate this beta, okay, if we evaluate the beta at beta t, so we're starting a point, right? Now, if we evaluate this beta at beta t, so then this is a okay. So if we evaluating L beta at beta t. This is using Taylor expansion, right? And if you apply the Taylor expansion to L beta at beta t, so what do you have? Then you have L beta t, right? Then plus the gradient L prime of this is beta minus beta t. This is first order, right? Then plus this L is so if you multivariate, this is involving a multivariate Taylor expansion. So if it's multivariate, then what you have here, then the L prime beta basically is DL beta. Oh, I actually have it. So you can have this is a U prime. U prime basically is the first order derivative of the beta from L beta with respect to beta 1 up to beta t, right? So you have here, this will just be U prime transpose times beta minus beta t. So this is a U prime, this is a vector, right? This is a beta minus beta t is also vector, right? Now the second order derivative is plus 1/2 of beta minus beta t times this is the second order derivative, which is going to be this h function, okay? From h. I'll go about that beta minus beta. Beta minus beta t plus some remaining term, okay? Let's just wave our hand here. The remaining term usually is in the lower order of this is the previous order, right? If you know the Taylor expansion. So let's just wave our hand to say this is a remaining term are not important, okay? It's important. We just get rid of because I'm not trying to provide a rigorous proof, but just give you the idea, right? So say, suppose this is your function L beta evaluating at L beta t, which is by using Taylor expansion. Then, if you want to maximize this function, okay, if you want to maximize this function, if you maximize this function, so if you maximize this L beta with respect to this guy, to the, let me just do this. So you want to maximize the beta, essentially is equivalent to maximize this guy, right? To maximize the Taylor expansion, the second order expansion. So what you're having here is basically you having, this is the beta, which is nonlinear on the left hand side. Now this become more like a quadratic form on the right hand side, right? So if you want to do that, then you're taking the derivative of the beta, of the d beta, okay? Derivative of this beta. If you want to maximize it on the right hand side. Sorry, this is the guys on the Zoom. I need to. Okay. So if you're making this is the second order Taylor expansion to the right hand side, you're going to maximize the L beta. Remember, you have a beta term here, right? You have a beta here and a beta here. So you need to maximize beta. So you want to maximize that. Then on the right hand side, then L beta, this is a constant term, it doesn't have beta, so it goes away. Over here, what you have here is going to be the it's going to be just u prime, right? Because this is going to u prime is the first order derivative of the beta, right? Is the first order derivative. Now on the second term here, if you're taking the derivative of the beta, then this is just basically q times the h times beta minus beta t. So what you have by q and the half going to cancel out. So what you have here is basically h times beta minus beta t. Okay. I should also giving this is ut because this is your this is your gradient valid at beta t, right? The gradient is valid at beta t. So you both of them, they're gonna have a t. They're gonna have a t in there to know this is your gradient and the second order. They are evaluated at this point as well. So in order to do that, you solve into if you want to maximize it, so you can have this is setting the first order derivative equal to 0, right? If you set the first order derivative equal to 0, you can see then your beta essentially is now the beta is solving for the beta, then the beta is going to be equal to you move this to the right hand side, so this will become negative. Okay, this will become negative ut prime. Then you're taking the ht, taking the inverse of it, and then moving to the right is going to beta t. Okay. So if you update the beta, okay. So let's call this beta t plus 1. If you update the beta from to beta t plus 1 in this form, okay, in this form, you will be able to making this, because what is beta t plus 1? Beta t plus 1 maximize this function, right? Maximize this Taylor expansion. So therefore, since it's maximize this is function, so therefore we're gonna have in this L beta t plus 1 is bigger than equal to L beta t, right? Which is satisfied our the original goal is we want to find a step such that we can update this beta to beta t plus 1, making this is beta L beta t plus 1 is bigger than equal to L beta t, right? So that's what it does. Now there are also the condition, because since it's the maximization, there's also condition to be satisfied. We need to check in this h is the sign positive negative, right? So it makes sure there's a second order condition. It also be there. So, but in this case, this is exactly why in here it is a minus sign here, because this minus sign to making this is because h is the sign negative what is it? Negative definite, right? So this is sign negative definite. So therefore, you have negative sign. This actually become positive. Okay. So this is actually is consistent with another claim, which is going to say in the gradient method is your function value always move if you want to is always increasing at the direction of the gradient. Okay. So this is the same thing because this is okay, this is sort of like the idea behind the different option. Is this clear or any question on this? Good. Okay, I again I weave I had a lot of hand weaving in here, okay, because I like for the over here I have there's some remaining term. I just assume I didn't really take good care of that remaining term, but in the rigorous part we need to see that. Then this is there are some conditions we assume like they are indeed have the first order and second order derivative and so on. So but this is if you can see this, okay, this is definitely give you the so like this slide is including the core idea about the Newton option. Okay, so if you even if you haven't really seen the Newton option before, I think this slide can provide a very good overview to you. So you can see what do we need to do here is we just need to evaluate the first order derivative, right, of the for the function L beta with respect to each beta I. In here we have a U prime, so this is our this is called a score vector, okay, something called score vector. So it's basically the first the order derivative of the log-like function with respect to the parameter. And you also have this Hessian matrix, right? H matrix, which is a Hessian matrix. In here is basically the second order derivative of the log-like with respect to the parameters. Now, again, this Newton option is a general method. It's not only applicable to the maximum log likelihood, it's applicable to almost like the any generic function, right? So this basically is a solution here. So if we can starting with some beta and we can update this beta t iteratively, okay, iteratively using this sequence, then it's guaranteed your likelihood function is going to increase in every single step until when you reach into to a point you cannot increase your function anymore. That's your maximum point. We already luckily, right? So for the log-like function, we already having this the first order and the second order the score vector and the Hessian matrix has been evaluated, right? Remember this is what we did here. Okay, we are setting up the problem. So if we plug it in, okay, this is a framework into the logistic regression problem. So what you can see essentially now is just basically what you are doing now is just the details, right? So we know the J's elements in the score vector, which is the first order derivative again, is equal to this guy, is equal to the summation I from 1 to n yi minus ni pi I t of xij. Now remember here, I have a t here. That is I assume I think this is the only thing I need to keep is let's just keep this formula in here. Beta t plus 1 will be equal to beta t minus Hessian matrix ht the whole thing inverse times this ut, right? Let me just keep this formula up here. Now remember your log likelihood, okay, your log likelihood L beta is a function beta, okay, but it's function beta. But we can also write in this is in terms of pi I, right? In terms of pi I by using this is exactly what we're showing here. By using here, you have this formula, okay? We can write it as a pi as well. Now the idea is, if you know beta t, okay, if you know beta t, then from beta t you can basically derive pi I t. Remember what is pi I? Pi I is the probability of success for each subject I, right? And the pi I is, because this is a pi I t basically is equal to e to the power of xi transpose beta t 1 plus e to the xi transpose beta t, right? If you know beta t using this logit function or the inverse logit function, you can have this pi I t, right? Now, if you have this is pi I t, then based on that, based on this is the formula we gave it in here. If you know the pi I t, notice here, xi is design max is given, yi is a response is, you know, is either 1 or 0. Ni you also know, right? It's, in this case, let's assume just 1. So if you know pi I t, then basically you know the uit, right? So for the first order, the derivative, you know that. And if you know that, then you also know this is a Hessian matrix as well, right? You can know that you know the Hij as well, right? So you basically know the score vector under the Hessian matrix. So if you know beta t, you know this component, okay? Now once you have in this component, then you can just plug in, okay? You can plug it back to here. Then you can update. You can plug in this component. You can update your beta t. Once you know the beta t, then you know pi I t plus 1 and uit plus 1 is gonna, and this is a cycle, right? This is a whole cycle is gonna you can still like iteratively proceed. So so in this case is if we when we having this, okay, when we having this is the ui or ujt is basically is a summation of this yi minus ni times pi I t times xij. That's why this is in this formula, although it doesn't have beta, the beta is embedded in the pi, right? It is embedded in the pi. So pi contains the beta we have here. With that, you can actually write in. So this is ujt. This is the function. It's just for one element, right? For the beta j. Now, if you write in the matrix form, the score vector, the matrix actually can be, if you can look at this just for a second, right? This is essentially just the x transpose y minus u mu t. Okay, x transpose y minus mu t. That's this is you can see this is you're doing the summation. So each one of them you are taking the one column of this xi, right? And then you multiply by because I from 1 to n this is subject. So you put all the everything together. In the metric form is just this is a score vector can be written as x transpose y minus ut. Okay, and what is ut essentially is just in this cases I'm just assuming here ut here the mu t. This is mu t. Mu t is equal to n times pi t. And if the n is a vector 1, so this is essentially this mu t is pi t. Okay, this is just in more like generic form. But you have everything in here. For the Hessian part, for the second order derivative part, we having this is a negative summation I from 1 to n xia xib times this component, right? So this is again is coming directly from the 2 slides before, right? We have derived that. So then this is if you want to write in the matrix form, okay? If you writing a matrix form, then this matrix form can be exactly is a quadratic form, which can be written as x transpose dtx, okay? Where the dt is equal to ni pi I t times 1 minus ni 1 minus pi I t, okay? So that's because this can directly from the formula above. So it's going to be the design matrix, the transpose design matrix times the diagonal matrix D with the diagonal elements going to be basically the variance of the yi. So then multiply by x again. So this will be This is our the function. So now we have what do we have here? What do we have? Ut will be equal to, so ut is equal to x transpose, okay, times y minus, let's just say pi t, okay, let's assume this this a is equal to 1, okay, I'm going to simplify it, it's equal to pi t. Then ht it will be equal to x transpose dt with the diagonal matrix x, okay. So what do you see here? Essentially, okay, what do you see here essentially is all the component for the Newton-Raphson algorithm. Okay, this is you have the ut, you have ht, you beta t, which is you kind of have everything. All you need to just to, if you plug everything into there, what you have is beta t plus 1 will be equal to beta t, okay, minus x transpose dt x, the whole thing inverse, times x transpose y minus pi t. Okay. Again, this is a pi t is equal to mu t. If ni is equal to 1, right? If this is n is equal to 1. This is so I'm just simplify the situation for you, right? This is the whole this is the algorithm behind it. Okay. Again, like I mentioned at the beginning, although the idea of likely function is kind of like the likely function is kind of like the look is like a little bit daunting, right? Is we have involving the product of a lot of terms, and this is you have this is you have to take the derivative and those things. But eventually, when you're working everything through, eventually what you're going to see is that you end up with a pretty simple formula. Okay, pretty simple formula. This is the this is like the beauty of the thing. If you come something pretty complicated, then there's a likely you have something wrong. But if it's this is like the beauty of the algorithm. So now the whole algorithm basically is work like this. You can choose in a beta 0. Okay, you can start in somewhere. This beta 0 could be like a random point. Okay, you can be a random point, or or you can have some like adequate guess if you have done this before. Like have some previous study, if you can have borrow information from previous study, you have some guesses. But it doesn't really matter. Okay, so you can start in within beta 0. This is you can be a random point. Then go through the iterations for each t from 0 up to some level, like some number, right? Like it's 100. So then we can calculate the pi it, which is by just plugging the beta t into this formula. Then we update the mu t, okay, and the dt. So this is our function, or pi t, right? Pi t. So then the beta t plus 1 essentially is equal to This is plus, right? Because the reason is okay, this is a plus, because this reason is here in the Newton-Raphson I have a minus the Hessian matrix, right? But in the Hessian matrix itself, okay, in the Hessian matrix itself, I also have a negative sign, okay? Because if this is a Hessian matrix actually equal to negative. This is a Hessian matrix actually equal to negative. Okay, this is a so this is my I sort of like skip this part. So this is you have a negative sign. So Hessian matrix is equal to negative x transpose dpx, which makes this is actually the sort of like guarantee. This Hessian matrix is the sign negative definite. This is the condition. So therefore, when you have in this algorithm, you have like a negative. This is equal to plus. Okay, this is a this should be a plus sign here. So beta t plus 1 will be equal to beta t plus this guy the inverse of the Hessian matrix, or negative Hessian matrix, multiplied by this X transpose Y minus mu T. And you're gonna continue, okay, and continue at every step. You're gonna evaluate the local likelihood function at the next step, and minus the local likelihood function at the previous step, and how much distance you can have. Okay, if this is the incremental is like a very small, you have this is epsilon. Epsilon typically we can choose in this epsilon to be like 10 to the -4, 10 to the -6. It's something very small. Okay, it's like something small. If your incremental is so like a become insignificant, okay, become very small, then you can pretty confidently say my beta has to reach to like a maximum point. So then you can stop the algorithm, okay? And this is how it works. Now for the algorithm, for the logistic regression, okay? For logistic regression, we have statistics have done a lot of work to evaluate this likelihood function, okay? We pretty much know the local likelihood for logistic regression is concave function, okay? Is concave. So if it's concave, that basically means if you're using this as the greedy algorithm, it pretty much is going to work, because now anything you find is a local, so-called local maximum is going to be global because it's concave function, right? So it's not a big problem for this application. But in case if you apply it to a new the like function, like in one of my when I was a PhD student, in the sort of problem I solved, the likelihood function is actually not concave. The likelihood function is of course is two-dimensional, right? It's actually have 4 modes. Okay, I can show you this. If you think about it as a square, the likelihood function actually has sort of like a peak at each corner of the square. So in that case, is if you have in that kind of like the non-concave the likelihood function, you may run into problem, because then what you find is that depending on your where you start. Okay, basically the initial point. This beta 0 is going to play a very important role, because if you're starting near the peak 1, you're going to find the peak 1. If you find near the peak 2, it's going to go here, and so on. So in practice, if you're not sure, okay, if you're not sure, what you can do is you can sort of like choosing multiple starting point. Okay, like if you can start, this is beta 0, is random. You can sort of like choosing multiple random starting point to see where they go. If they all convert to the same point, okay, then this pretty much give you confidence. Say this is at least that maximum point is covered large range, right? But if you having this is if you go to different places, then you examine like what do you want to do. Then you want to choose in the global maximum or the local maximum, or then that's well, you have to do some further digging, okay, investigation to do the problem. Typically, even your algorithm didn't go to the global maximum, okay, even if it can go to the local maximum, it's still useful, okay. That means the it doesn't mean the local maximum is worthless, okay. It's still better than you don't optimize it, but it's just not optimal point. So in reality, many times we do settle with a suboptimal solution. Okay, in most cases, getting the job done is probably better than the getting a perfect solution. Okay, remember, you guys probably know the 80-20 rule, right? So if you can spend like a 20% effort, you have get 80% of the job done, then the rest of 20% of the job is probably taking you like 80% effort. So in terms of the efficiency, sometimes you may want to just satisfy with this is like 80, right? So within the minimum effort, 20% effort, you're getting like 80% of the effect or the 80% of the productivity done, then you can for the 80% of effort you can spend on something else instead of making it perfect, right? So that kind of philosophy applies into modeling as well, okay? Because then if you want to you end up sometimes you end up within the one local solution. That local solution is already can achieve like 80% of your goal, then that may be good enough. Because if you want to find a global maximum, you have to try a lot of this random point, and this is computing expensive, right? So particularly in big data, every time you run this algorithm, it took a lot of resources, so it may not worth it. So this is but again, this is just some it's not really related to algorithm, but it's more like on the practical side. Okay, so this is the algorithm. Any question on this? Okay, so the algorithm works pretty good. Is pretty elegant. There's one thing still kind of not really there's one thing is still kind of bothersome, which is the H part, which is the Hessian metric part, right? Because the Hessian matrix is the in here you to compute a Hessian matrix. Remember the D matrix is still a large matrix, right? It's still like a D is n by n matrix. X is a P by n matrix, right? So to compute a Hessian matrix, you still need to do a lot of computation, okay? A lot of computation, and you also need to do the inverse. Now, before I go to that, there's actually one little thing I want to mention is so there's a small note before we go to the gradient method is the covariance matrix of the beta hat is actually equal to x transpose dtx inverse. Okay, so this is actually the byproduct of the neutrality method, because you see when you want to update this guy over here, if you want to update the beta t, you already have this value being calculated. Okay, so in another word, the covariance part or the variance of the covariance of this beta hat has already been computed in the algorithm. So it's kind of like the free lunch. This is in order to get beta t, you have to calculate this thing, and if you have this calculation, you already have it. So you are not just making the inference, but you kind of not having point estimation or have the variance part already. So that's kind of this is kind of nice. Now another thing I want to show you guys is this thing. Which is I think it's pretty elegant, okay? Now if we have this beta t plus 1, let me just rewrite it, okay? Equal to beta t plus this is the x transpose dt x equal. Let me see from the okay, you guys can see x transpose y minus pi t. Okay. Now let's do some further evaluation. If we multiply, okay, both sides by the x transpose dx, okay. So what you're gonna have here is x transpose dt x times beta t plus 1. Right? This is going to be equal to x transpose dt x beta t for axis here. Then the second term on the right hand side, this is gone, right? This is gone. You're going to have xt times y minus pi t. Okay. This is clear, right? This is simple. So what I did is just multiply the xt dt x transpose dtx on both sides, and then this term is gone. Now, if I multiply, okay, if I multiply dt and its inverse on both sides, okay, in the second term, I didn't change anything, right? This is the identity. This is the identity matrix. Remember, dt is a diagonal matrix. Its inverse is very easy to evaluate, right? Inverse just to inverse is every diagonal value, right? Now, on the right hand side, now I have the xt dt. This q thing is I can take it out, right? So what we see here is going to be x beta t plus dt inverse y minus pi t. Okay. Now I can multiply this back again. Okay. Then to having this, I have beta t plus 1 will be equal to x transpose dt x inverse x transpose dt. Let's call this thing to be zt. Okay. Why do you want to do that? Okay, why do you want to do that? From this, can anybody recognize like what is this form? Anybody recognize like what this is what this looks like? Remember, dt is a diagonal matrix, right? dt is diagonal matrix. Anybody recognize what it is? Now, if I remove the dt, okay, if I remove the dt, x transpose x inverse x transpose z. Anybody recognize this guy? If I say beta t plus 1 is equal to this thing, what does this look like? The down below here, this is the kind of solution of the linear regression, right? If I do zt regress on x, then this is the coefficient for x, right? So, but now I have a dt in up here. So what this is also okay. This is also representing linear regression, but this is called weighted linear regression. Weighted linear regression. Okay. So within the weight essentially is just dt. Okay, with just dt. So the solution in the above over here, this is actually you can say is a WLS is a weighted least square solution. Okay, it's a weighted least square solution for the regression for the linear regression within the weight applied to each one of them. Now so this is basically what I showed you. Beta t can be written into this form, and with the zt essentially is going to be equal to the log of this pi zit. Okay, for the s elements of the zi is equal to this is a log pi I over 1 minus pi I plus this guy over here. Now this is indeed the weighted least square form. So what does this mean? This means for each iteration in this logistic regression, for each iteration in the algorithm, it is indeed just a weighted least square. Okay, it's a weighted least square. So we break it down long linear problem, which is maximize the log likelihood function for the logistic regression. Now breaking down into a sequence iterative algorithm, and each step is indeed just a linear solution. Okay, is a linear regression problem, and you can solve the linear problem within within the MapReduce for the big data. You know how to solve the linear problem. We already talked about it. So here essentially is the logistic regression. Now you just apply, we just having, say, solving the linear problem for big data is a MapReduce job. Now in here, what you do is just iterative MapReduce. Okay, that's how you can see it. Here there's actually more. So the ZIT, the ZT, right? Remember the ZT, the ZIT, okay? Each element of the ZT, what is look like? Because each element, this is x beta t, so this actually is going to be xi transpose beta t, right? Because if you're taking the ith element of the z coming from this matrix form, each of element of ZIT is just basically xi transpose beta t, right? Plus this is the term which is essentially the dt, the diagonal matrix of the d. What is d? You remember the d is this is ni times pi I 1 minus pi I, right? This is this form. So this is equal to the log, is basically the logit of the pi I, which is log of pi I t over 1 minus pi I t. Remember, this is a logistic regression, right? Xi beta is indeed equal to this guy. And then for this yi, for this denominator here, this is basically yi minus pi I t in the numerator. Denominator is this diagonal matrix inverse. The diagonal matrix at item I at ith position for this diagonal matrix is indeed the pi I t times 1 minus pi I t. Okay, so this is where in here this is ZIT, this is come from. Okay, this is where it comes from. So what you do here essentially is at every single step, okay, at every single step is indeed ZI, which is the you can have this ZI, right? Is Z regress on X with the weight dt. Okay, that's how the whole thing is work. So the algorithm called for solving for logistic regression, it also has another name. It's called the IRIS. Okay, iteratively reweighted least square. So iteratively reweighted least square. Why is called the IRIS? Because first of all, I is called iterative, right? So because the adoption is an iterative process. That's you know. Then each step is a weighted least square, and then this weight, okay, is also changing because at each step your weight is depending on the pi I, right? Your dt is dependent on pi. So that's why it's reweighted. Okay, so the IRIS is this is the iterative reweighted least square. This is sort of like the name for the algorithm. If you in the future if you heard of this iterative reweighted least square, you know that's a solution for the logistic regression. This is just a reminder to you, say why this solution is indeed solution is you have a z is regressed on beta x beta plus epsilon. Within say the covariance of epsilon is v. Okay, v is like in the general sense. Then the solution for the beta hat is equal to this thing is a weighted least square estimates. I can just take like I can just take 1 minute, okay, to show you why this is true. Say you have z is equal to x beta plus epsilon, and say the epsilon is follow normal with mean 0, and the variance is going to be v. Okay, v here could be diagonal. If it's diagonal, that's essentially the effect is apply weights to each subject. or the V could be just like in general, it is a general matrix. Okay, let's talk about the general case. So if you have in this V to here, what you can do is you can essentially times the V inverse, okay, to the Z. Half of inverse, okay. Now this has become like a little bit more involved because then what is the half of Z? Let me just finish this is the first. Then if you're interested, I can talk about it. So let's define the Z star equal to the inverse of the V, half inverse of V times Z, and this is you're gonna have in a new X star, which is equal to this guy times beta plus epsilon star. Okay. In this case, once you do this transformation, basically the epsilon star is going to follow a normal 0 with an identity matrix. Okay, so if you multiply, if you know the V, okay, if you know the covariance matrix of epsilon, if you multiply half of the inverse of this V on both sides, essentially you can end up with this guy. Okay, the down this is star form. This essentially is a linear regression form, is a regular linear regression. Okay, so the solution for the beta in this case, we can just write the beta hat is just equal to X star transpose X star inverse times the X star times the Z star. Right? Essentially just everything. Now, if you plug in this is X star into here, then inside here is just be X transpose V half, because V is a covariance matrix, is symmetric, so transpose is just itself, times V half of X inverse times this is the X transpose V half times V or minus half. You will have minus half, V negative half times Z, right? So then, which is become X transpose V inverse X, the whole thing inverse times X transpose V inverse Z. So this is how you have in the, if the V is diagonal, then this has become like exactly the form we have here. What is V inverse? V inverse is the diagonal is very easy to understand. So this is just basically you taking the inverse of the diagonal elements, and you take the square root. That will be right. So in general case, if your V is not inverse, then because V is if it's covariance matrix, okay, you can actually decompose it using the single value decomposition. It can be decomposed as the P transpose times D times P, okay? Or you can decompose into the matrix into this form. So V inverse is essentially D half times P, okay? This is the V inverse. There are some definition for this. I'm not going to go into detail because that's it's not a focus in here. But just in case you guys are curious, how do you get in like a half of the inverse for the matrix? Okay, this is how you compute it. Okay, so this is what I want to say about the iterative reweighting. So here, iteratively reweighting this square, right? So this is algorithm name. Basically, it's a maximum likelihood solution for logistic regression. Okay, so hopefully by now you guys knows you can confidently say now for the logistic regression, you not only just to be able to like call the function, okay, but know the mechanism actually behind it. How do you get in this estimation? Also, even including how to get its variance term. Okay, it's all here. There's one thing. Okay, there's one thing for the neutral option is everything looks nice, everything is good, and we can, if you want to compute it, we still can be able to do it. Now there's just one thing is kind of like I said, is kind of bothersome is this is Hessian matrix. Okay, Hessian matrix, if it's large, if data is large, then compute a Hessian matrix is ahead. Okay, is ahead because it's involving this is the quadratic evaluation for this thing. So if you can somehow avoid the Hessian matrix, this is computation. Okay, that would be preferable. This is indeed this is we can use an idea of this called gradient descent. We can also have in this is we can solve this as well. Now it also comes with a price. Okay, Newton-Raphson you can pretty much prove. You can prove it. Okay, it's first it has a guaranteed convergence. Second of all is the convergence is very fast. Okay, it's very fast. Just on the cavity you have to deal with the Hessian matrix. Gradient descent is another way. It's still having that like Newton-Raphson is a special form. It's a gradient descent. Okay, but the gradient descent is also works. Now the gradient descent is based on the observation that if for multivariate function fx, okay, is defined and differentiable in a neighborhood of point like in a point A, then this function fx decrease fastest if one goes from A in the direction of the negative gradient of f at A. So if you have in a fx, right, you can evaluate in the gradient. Gradient essentially is the first order derivative, right? In our sense. Now let's just so if you have function fx, and if you have point A, then you can define the gradient of fx, which essentially is derivative of fx regarding to the x1 and fx. Oh, this is not partial derivative. This is partial derivative, right? So it's a partial derivative of x say p, and the evaluate x equal to A. Both x and A are vectors. Now, the gradient says the fx decrease fastest at the negative gradient of f. The other way is also true. Okay, the value of fx increases fastest if at the direction of the gradient. Okay, so this is just like the two sides of one coin, because maximization and minimization, they are the same thing, right? Because if you want to maximize a function, basically is equivalent to minimize the negative of this function. So if you want to maximize L beta, this is equivalent to say you want to minimize this negative L beta, right? So these two things are identical. So if you can solve the minimization problem, you can do the maximization. Basically saying if you have point A, okay, then if you go to the direction move the A into the direction of the gradient, negative gradient. So it's A minus gamma times gradient FA. Gamma is bigger than 0, right? Gamma is positive. Then if gamma is small enough, you can make sure your FA is bigger than equal to FB, right? The idea is also the same. You can say this is fx. If you evaluate FA, then is let's say just using the first order derivative. So then this is going to be the gradient of fx times xa, x minus a. Right? Now, if you evaluate the b, say b is equal to the A minus gamma times gradient FA, right? So what I have here is FB is going to be equal to FA. Again, I have some like a many term, okay, I ignore it. Plus, then this is going to be gradient of FA times B minus A. Okay, so what is B minus A? B minus A is the negative gradient. So B minus A in here is just negative gradient of FA. And we know this is sort of like a dot product, right? It's kind of dot product, two vectors. This has to be bigger than or equal to 0. So therefore, then we have here is going to be say FA has to be bigger than FB. Okay? So the B is if you go down into the negative gradient, your function is decreasing. So the same thing if you go into the function, if you go in direction of the gradient, so this is if this is positive. Right, if it's positive, then FB is going to be bigger than FA. So if your function is going to increase in and the direction of gradient. So this is sort of like the gradient descent, the method. So with this in mind, we can always start in the algorithm saying we can start from some random guess x0 and then we can do this is the x n plus 1 equal to xn minus gamma the times the gradient of f(x)n. Then this is hopefully this is going to converge to some local maximum. If you look at this is if you look at this form, right? So in the so if you look at this, apply this form, and if you apply to logistic regression for the gradient descent, we only need the first order derivative, right? We only need the first order derivative. So therefore, you only need the ut, which is already given. So for the gradient descent applied to logistic regression, what you're going to do is going to be the first term. The first part is the same. We're going to randomly starting somewhere, and then at each time t, we compute the pi t for each one of them, right? So then we compute this is which give you our the first order the derivative. Now we update the beta t. Is beta t plus gamma times x transpose y minus mu t. Until this is longer the improvement. Now notice here I'm using plus here instead of the minus because I'm trying to maximize my likelihood, right? I'm trying to maximize likelihood. So therefore I'm using the moving in the direction of the gradient. Now if you compare this guy within the Newton-Raphson we have in a few slides ago, what we do is we replace this Hessian matrix within this Hessian matrix within the gamma. Okay, within the gamma. So what you do here, the gradient here, you see here, everything else is the same. Instead here we have a Hessian matrix. We have a scalar gamma. Okay. Now this is for the gradient methods. Apparently, computation is much easier because we avoiding this Hessian matrix the hassle completely. We don't have this deal with the Hessian matrix at all. Now it also comes with a price. Okay, this is come with price. Because the question is, how do you choose gamma? Right? What is the value of the gamma? What is the value you're going to choose? So the gamma is we have a term for it. It's called step size. Okay, step size means how far away at each time you want to move your beta away from the previous the value. Apparently, if the gamma is large, right? The gamma is large. You're gonna taking a large step, right? You're gonna say the gamma is large. Then every time when you have this is a beta, you update the beta to the new value, you're gonna have a big change, right? You have a big change. If the gamma is small, then you're gonna have a small change. Now, if your gamma is small enough, okay, if gamma is small enough, it's guaranteed your algorithm is gonna converge, okay? If the gamma is small, you guarantee it converge. But the price is it may taking a long time. It may taking like if you're taking the gamma, say gamma is -6, okay, at 0.00001, is very small. So every time you take a tiny step, you guarantee you're gonna every time you're gonna increase your like function a little bit. But this is the iteration may taking like a 10,000 times. It's very computationally inefficient, right? Now, if your gamma is large, say if my gamma is 10 to the 6, it might take my gamma is large. That's also create a problem because think about if you having think about you have this problem. If you say you're starting from somewhere here, beta t, then if your gamma is too big, you may move away. You may getting up to your moving point may be over the maximum point, right? So then if your gamma is too large, it may create a problem called oscillation around the maximum point. Because once you get into this point, The next time you may also kind of also do that on the back and forth because you always try to move into the direction of the because this is gradient can only tell you go that way, okay, go that way, but it can tell you how much you're gonna go. So although this gradient method sounds like seems easier, but it has in this is the problem how to choose gamma. The gamma, the choose of gamma, there's a tons of research on this as well. Okay, the typical thing is at the beginning of the search. Okay, at the beginning of search, see that the beta 0. If you don't have no idea, you want to be your step size gamma to be big because you want to take a big step, right? But as you're getting closer to the point, to the maximum point, you want your step to be small. Right? You don't want to be too big because if you're already getting close to this open point, taking a big step maybe getting way off, right? So then in general, the choice of gamma, you try to say is you want to be big at the beginning of the algorithm, then gradually go down to be a smaller value. Okay, there are some theory behind it to do that. Or you can also do so-called line search, okay? Because at here, each step you can actually search for like which gamma gonna give you the best incremental to that. So there are other ways to do that. But in all practice in this way, because we are not really is the detailed algorithm, right? That's a separate course. So in our application, we can just assume gamma to be like a small value. Then we can do that. Okay, so that's enough today. So next class we're going to talk about how to implement this algorithm, okay, with MapReduce, and then after that we're gonna move on to like ADS, get a setup for the ADMM and so on. Okay, that's all for today. I'll see you guys next Monday.